What's boppin', hep cats? The night is young and I am ready to jam. Except all the disco clubs are closed because of the novel coronavirus. Could you believe that? A cool cucumber like me stuck here at home? There's hardly any room for my bell-bottoms.
Dance floor is full.
Sometimes, though, even when the clubs are open, I can't always get into them.
Dance floor is full.
Sometimes the dance floor is full.
It is for you.
But I don't let that get me down. Not at all. As a matter of fact, it helps me relate to my research. You see, when training a deep learning model, a tensor can also find that the dance floor is full, so to speak. That is, the memory for storing tensors can be limited. Training a model requires performing millions of inferences on sizable training sets and adjusting its parameters via backpropagation. Backpropagation, or propagating the error through a model, in turn, requires storing intermediate activations in the model. This is by far the largest use of memory when training a model. Memory usage can be a significant bottleneck when trying to train models using accelerators and other specialized devices, since these devices are limited by their built-in memory. Such limitations prevent training larger and deeper models efficiently. So how does a deep learning model keep on stepping? One technique to reduce the memory used by intermediate activations is checkpointing, which trades computation for memory by recomputing activations instead of storing them. This can be a desirable trade-off if relatively few additional computations are needed to save considerable memory. Many past approaches to checkpointing in deep learning have been successful in achieving a balance between recomputations and memory savings, but they have done so by statically planning all the memory allocations for a model. Typically, this is done by dividing a dataflow graph into segments and recomputing each segment, storing only the state needed to run that segment. These decisions require knowing all the model's control flow in advance, which prevents applying these techniques directly to more dynamic models. By contrast, the work we are presenting makes decisions about which tensors to store and recompute dynamically, hence Dynamic Tensor Rematerialization, or DTR for short. DTR acts like a domain-specific cache, allowing allocations to proceed until there is no memory left, at which point DTR uses a heuristic to choose tensors to evict. The goal of the heuristic is to choose something like the largest, stalest, and cheapest to recompute tensor. This means the system only has to store a little metadata per tensor, namely the last access time and the time it took to compute the tensor. A huge advantage of the deep learning domain is that tensor operators are expensive and monolithic, so the system overhead is likely to be very small compared to that of operators. Most importantly, DTR avoids making any assumptions about models, so it should be possible to transparently apply the system on top of dynamic models. This graphic shows the behavior of DTR on an n-layer feed-forward network, showing the lifetimes of tensors as they are evicted and recomputed throughout the execution of the model in both the forward and backward directions. The color scale denotes the heuristic value of the different tensors. That was a demonstration of a simulator we wrote to help us understand how our heuristics perform on a variety of models. We are presently implementing DTR as a memory management system in PyTorch, allowing it to save memory on a variety of dynamic models on real workloads. And DTR will certainly keep me busy until the day I can finally return to the disco.
Dance floor is full.
Disco will return.